My name is Amber Marsh, and today I will be presenting my final project for ADTA 5550. The first part of this project involved finding a data set of either images or audio files on a public domain. I was able to find this data set that involves animals, and it was created by Querido Alicio. I also found this on Kaggle.com. So if we go ahead and look at it, this is where I got it from. You can see that this data set has 28,000 images of different animals. The animals belong to 10 categories, which are dog, cat, horse, spider, butterfly, chicken, sheep, cow, squirrel, and elephant. The data is very well organized and would be perfect for CNN models. It could be used by identifying key features of said animal and then being able to categorize them to their specific species. This data has multiple images along with image types. There are 24,200 JPEG images, 1,919 JPG images, 51 PNG images, and then one which is classified as other. This could be very useful for individuals who are in the biology field, which could allow them to perform research in specific animals they may specialize in. So part 2 of this project was to obtain the CIFAR-10 dataset and upload it to our Jupyter Notebook. The first thing we had to do was go to our remote Jupyter Notebook. After we're there, we were able to create a new folder, which is shown in the screenshot to the left, called CIFAR-10 data. Then we click that folder, and then on the screenshot on the right, you can see this little upload button on the top right-hand corner. Once we click that, we're able to upload all of these files which we previously downloaded from Canvas. These files include data batch 1, data batch 2, data batch 3, data batch 4, data batch 5, test batch, and then batches.meta. After this, we would click upload, and then we have successfully uploaded this data set to our remote Jupyter Notebook. So now when we go into our model, we can reference it and use it. So part 3. For this, we will build, train, and test CNN on the data set we just uploaded. Before we start to build, train, and test our convolutional neural network, we need to import basic libraries into Python. This will allow us to correctly analyze the CIFAR dataset and make sure it is shaped correctly. It is important to note that each image is using the one-hot format. We will also be splitting this dataset into training and testing to perform more accurate analysis. After all the pre-processing to make sure our data is set up correctly, we're now able to define supporting functions. This involves initializing weights as well as bias. The first one stores weights in a filter by getting random numbers. It allows us to initialize weights by using TensorFlow variable. Initialize bias is similar to the previous one, but correlates to TensorFlow variables for bias. As you can see, these codes are shown in the screenshot. So after this, we need to set up a convolutional layer and perform convolutional computation. This involves defining the function, initializing the weights, then create the convolutional layer. To create this layer, we have to specify the shape, which is already known. We then are able to obtain the convolutional layer outputs. After this, we are able to do the same thing by creating a RuLu layer instead. In this layer, we will create it by specifying the shape as well as returning the layer outputs. This layer is an activation function and also has weights that are initialized. This is all shown in the screenshot on the screen. After this, we need to create another layer, which is the pooling layer. Just like this, we need to define the function as well as reduce the spatial size. This will reduce the size of the inputs, which are the outputs of the RuLu layer. We also will have to define the shape in which we already know. And just like the other layers, we will return that layer. This is shown on the screen. Then we are able to set up a fully connected layer to start to perform the computation. This too forces us to define the function which correlates to both inputs and output size. We then are needing to get the number of inputs, which is coming from the size of the image. We then initialize these weights and biases just like all the other layers. We are then able to compute the fully connected layer by multiplying inputs by W. After, we are able to return the outputs as you can see. So after those layers are specified, we're able to build the convolutional neural network. The first step of this includes creating placeholders for inputs and the labels. This ensures that it is a 2D array and specify that each row is a vector. This allows us to specify the shape of X and Y. We can then reshape the input placeholder to help us feed the data into the layer correctly. This is shown on the screen right now. So after this, we are able to create the full convolutional layer, RuLu layer, and then perform the computation. This function uses the outputs of the convolutional layer. We then are able to create the first pooling layer and reduce spatial size. This creates outputs from the first pooling layer while also reducing the spatial size. We're then able to perform the steps to set up the second convolutional layer as well as the second pooling layer. This action is shown in the screenshot below. So now we can finally go on to the next step, which is reshaping or flattening the data. So now it is able to be fed into the first fully connected layer. This function is shown in the screenshot on the screen right now. We can see that the data being inputted is the previous codes that we just saw before. It returns the outputs of the products being multiplied. After this, we can create a dropout layer. This will happen randomly, so when it's performed, a certain percentage will be ignored in the next layer. After this, we can create a final fully connected layer, which gives us the final outputs. We specify that the final output layer is 10 because that is the total number of classifications we are needing. We're then able to compute the outputs from this layer. So after this, we can define the loss and calculate the loss function and calculate the softmax cross entropy loss. This function uses the predicted final outputs from our previous code. It will perform the function by using the means of all the values to get the loss value. We then can create an optimizer and create a trainer. We specify the learning rate is 0.001, and then we can train it by using the minimize function. This is all shown on the screenshot on the screen. So finally, after all those steps and requirements are met, we can use this to train and test the model. First, we need to specify that there are 5,000 total steps. We also need to specify that we are only using the initialized values which we specified before. We then are able to specify that each batch has 100 subsets, and then we can run this code to train the model. This includes the dropout layer, as well as comparing to see if the predicted value and actual value are equal. We are then able to test the model, which is shown by the accuracy percentage. So as you can see, the screenshot on the right, it says currently on step 0. That shows that step 0, the accuracy is only 0.1039. If you go further down though, which is shown the screenshot below that, you can see that for step 4,900, the accuracy rate is 0.6953. This is a huge increase in accuracy from step 0 all the way to 4900. We can easily see that over time the model improves. However, having an accuracy rate of about 70% is really not that great of a model. This will lead us directly to the next section of the report where I will try to improve the model's accuracy. So now for part 4 of the project, we're comparing the CNN from our previous project we just completed. When we did that, we used the MNIST dataset. The screenshot shows both the accuracy rate for both of these datasets. We can see that when the step is 0, which is highlighted in blue at the very top, the data sets are pretty close. When looking at the accuracy rate, there's only about a 3% difference, which isn't that much. But as you start to further look down the table, and then if you see at the very bottom on step 4900, this is highlighted in blue too, you can see the final accuracy rate for both of the models. The MNIST dataset has 98.95% accuracy rate, which is a great model. However, the CIFAR dataset has only 69.53 accuracy rate. This is about a 30% increase in accuracy rate when comparing both models. We can see that throughout the process, the MNIST dataset always outperforms and would be the best model to choose in this situation. Some reasons to explain this would be the data that is in these sets in general. When working with the MNIST dataset, we had less variables and not as many parameters when specifying our output length. For the CIFAR dataset, we had much larger dataset and also had many other factors that the other one did not. There were more things running in the background in order to make sure the output variable was easily understandable. The dimensions for both models were very different, and due to this, one model might have been easier and faster to process. Many factors go into these models and have multiple layers and can possibly create even more complications. With less parameters, the machine is able to process and learn information simultaneously. This further explains why the accuracy rate is so high for the MNSIT dataset instead of the CIFAR. But you also have to think that because of this, it could have potentially overfit the model. So now we're going to take a step back and focus on what we did in part 3 for the CNN. If you remember, we got the accuracy rate of 0.6953. As you're shown on the screen, now this is the model I use to perform or try to improve the accuracy rate. And I will further discuss all the steps I did to do that. So just like last time, we had to process the data to make sure it was set up correctly. We now are able to use the defining supporting functions, and this involves initializing weights as well as bias. The first one stores the weights in a filter by getting random numbers. It allows us to initialize weights by using TensorFlow variable. Initialize bias is similar to the previous one, but correlates to TensorFlow variables for bias. Excuse me. After this, we need to set up the convolutional layer just like last time and perform the convolutional computation. This involves defining the function, initializing the weights, then create the convolutional layer. To create this layer, we have to specify the shape, which is already known. We then are able to obtain the convolutional layer outputs. After this, we are able to do the same thing, but create a RuLu layer instead. In this layer, we will create it by specifying the shape as well as returning the layer outputs. This layer is an activation function and also has weights that are initialized. This is all shown what we did previously. After this, we need to create another layer, which is the pooling layer. Just like this, we need to define the function as well as reduce the spatial size. This will reduce the size of the inputs, which are the outputs of the RuLu layer. We also have to define the shape in which we already know. And just like the other layers, we will return the layer. This is shown in the screenshot from the previous section we already discussed. We are then able to set up a fully connected layer and start to perform computation. This forces us to define the functions which correlate to both inputs and output size. We then are needing to get the number of inputs, which is coming from the size of the image. We then initialize weights and bias just like all the other layers. We then can compute the fully connected layer by multiplying the inputs by W. After, we are able to return the outputs just like we did last time. So after those layers are specified and set up, we can build the convolutional neural network. The first step of this includes creating placeholders for inputs and the labels. This ensures that it is a 2D array and specifies that each row is a vector. This allows us to specify the shape of both X and Y. We can then reshape the input placeholder to help us feed the data into the layer correctly. So once we do that, we can finally use this to create the first convolutional layer, RULU layer, and then perform the computation. This function uses the outputs of the convolutional layer. We are then able to create the first pooling layer and also reduce the spatial size. This creates outputs from the first pooling layer while also reducing the spatial size. We are then able to perform the exact same steps we did in the last time. However, we are removing the second layers. We're not going to have a second convolutional layer. We're not going to have a second RULU layer, and we're not going to have a second pooling layer. This was my attempt at trying to create a model with a more significant performance or increase its accuracy rate. So with that, although it's a little change, it is slightly dramatic because it changes the way the diagram and the model works as a whole. You are deleting a whole layer, which could potentially cause problems or create solutions. So after that happens, we can then go to the next step, which is slightly similar to what we did in the previous model. This step is to reshape or flatten the data. So now it is going to be able to be fed into the first fully connected layer. This function is shown in the screenshot below, or the screenshot previously shown, sorry. We can see that the data that's being inputted from the previous codes are the exact same, however, there are slightly different tweaks. Like I said before, we don't have the second layer, so now all the code will be referencing the first layer. This also, like last time, will happen randomly. And it'll happen randomly, so when it's performed, only a certain percentage will be ignored in the layer. So then we can finally create our fully connected layer, which will give us our final outputs. We specify that the final output layer is 10, just like last time, because that is the total number of classifications. We are then able to compute the outputs. So after this, we still need to create loss functions, calculate softmax cross entropy loss, create an optimizer to optimize, set learning rate, and we also still need to create a trainer. So to define the loss function and calculate the softmax cross entropy loss, this function uses the predicted final outputs from our previous code, but it will perform the function by using the means of all the values to get to the loss value. We then are able to create the optimizer to create the trainer. We specify the learning rate is 0.001, just like our last model, and then we can train it by using the minimize function. So now, finally, we're able to train and test the model. Like I said before, we only have one layer. We don't have the second layers, but we also changed the number of steps. Instead of 5,000 steps, I changed it to 7,500 steps. Those will only be using the initialized values, and they're still, just like last time, each batch will have 100 subsets. So we then run the code to train the model. This includes the dropout layer as well as comparing to see if the predicted value and actual value are equal. We are then able to test the model, which is shown by the accuracy percentage that you guys have seen this whole time. At step 0, you can see that the accuracy is 0.1176. At step 7400, the accuracy is 0.6437. So actually, this attempt at trying to improve the performance actually failed. We were not able to get a better performance by removing a layer, which is very important to know for future use. You have to really know how a model works to understand the effects it might have. Although I tried multiple situations, this was actually the best accuracy rate that I personally could get. So, another thing to note is because we only have one layer, one convolutional layer, when we set it up before doing the computations, the shape was still the same and the reduction of the spatial size was still the same. But the difference is that the way we reshape the data, because the size actually changed because it's 1 instead of 2. So the parameters for that was -1, 16, 16, and 32. This could have a huge difference on the accuracy rate because it is a smaller size than what it was predicting before. We then So because of those little tweaks and those issues, we could see how the performance or accuracy rate changes depending on what you do to the model, especially if it's using this data set with so many variables and so many factors. This is a very important message or lesson that I learned because it's very important to know how your model works if you're wanting to change the structure for any reason. So in this project, as well as life itself, it's important to understand as much as you can about a topic before you start to change stuff. Having more knowledge allows you to have more power or more capability to potentially improve the situation. Thank you for watching my presentation.